In this video, we will be looking at how to graph polynomials when they are in factored form. So here we have the function f at x, and it is in factored form since we see all of these factors, all these brackets attached by multiplication. The first thing we might want to do is identify our zeros. And just a reminder, when you are finding your zeros, you're just taking each factor, setting it equal to 0, and isolating for x. So for example, the first factor is 2x. If I were to set that equal to 0 and divide both sides by 2 to isolate for x, I get 0. So there's my first x-intercept at the origin. I can do the same thing for the next factor, x minus 3. I set that equal to 0. When the 3 moves over, it goes from negative to positive. So there's another x-intercept. And I can do that for all of my factors. So for x plus 1, we have negative 1 comma 0. And for x plus 5, negative 5 comma 0. And then we can go ahead and plot these values. The origin at 3, at negative 1, and negative 5. We also want to take note for these zeros if we are just passing through, if we're jumping off of the 0, or if there is a point of inflection at that 0. So for the origin, we're just passing through. For the 3, because it is an order of 2, we are jumping. For negative 1, it's an order of 3, so that exponent of 3 on top of the factor means we have a point of inflection. And finally, at negative 5, we're just passing through. Now that we have our zeros, we can also find our y-intercept. For this one, our y-intercept is quite easy. Because one of our x-intercepts is the origin, that is also our y-intercept. However, if that weren't the case, your y-intercept just comes from setting x equal to 0. So if I were to take all of those x's, substitute a 0 in, and evaluate, I would get 0. And there we are, that's already plotted. The next thing, we might want to look at the degree and the leading coefficient just to get an idea about our end behaviors. So for your overall degree, you want to take all of your exponents and add them up. Keep in mind that there is invisible 1 exponents. So 1 plus 2 plus 3 plus 1. Our degree is 7, which means it is an odd number. We're going to have opposite end behaviors. Now our leading coefficient is positive. That just means if you combine that with the fact that we have an odd degree, you're going to have a function going in this direction in quadrant 3 to quadrant 1. I mean, it's going to be a lot fancier in the middle here. Obviously, it's not just a line, but that is going to be our general trend for this polynomial function. Now, the last thing that I want to obtain here, my extrema, whether they're absolute or local max or mins. As a reminder, at this point in time when we are finding these max and min values, they are estimates. We will get accurate numbers once we get into calculus in the next course. But for now, we will be estimating these values. So I like to just make myself a little number line here, put my zeros in correct order. So -5, -1, 0. and 3. And my estimate for those local max and mins or absolute max and mins is to take the average of the 0. So find the in-between number between each pair. So between -5 and -1, the average of these numbers, so just adding them and dividing by 2, is -3. So I'm going to evaluate what is y when x is -3. Between -1 and 0, halfway is -0.5. And finally, between 0 and 3, halfway is 1.5. So now I'm just going to go into my function and evaluate f at -3 for my first one. So the long way here, 2x, but instead of x I'm putting -3, x minus 3, so -3 minus 3 squared, x plus 1, so -3 plus 1 cubed, and x plus 5, so -3 plus 5. And this I would just punch into my calculator all in one go, and I get 3,456. So there's one of our coordinates, -3, 3,456. And I can do this for the other ones. So if I evaluate f at -0.5, punch that into my calculator, I get approximately -6.89. When I evaluate f at 1.5, again in my calculator, I get approximately 685.55. And I like to get all of these estimates first before I label my y-axis. Now I have an idea of what the highest and lowest number should be for my very rough scale. So looking at this, I have a number 3,456, that's my highest. My lowest is -7. So now I have an idea that maybe I'll do every tick mark on the y-axis is going to be 1,000. So I have 1,000, 2,000, 3,000, and 4,000. And then here's -1,000. And that's all I need to label, and now I can plot my points. So I'm going to start with -3, 3,456, just estimating it over here. At -0.5, we are going to be super close to the y-axis because it is just around -7. And with this scale, we're pretty much just touching that y-axis. And then finally, we have 1.5, 685, so somewhere here. Now I have to keep in mind that I have a jump at 3, and I also look at my end behaviors. This is the trend I'm going to have. So I'm starting here in quadrant 3. I'm going to pass through some things, and at 3 I'm going to jump up to stay in the positive. So I have an idea of how I'm going to connect this. So a jump at 3, and also a point of inflection at -1. So when I come down from this local maximum, I'm coming down and I'm going to do a little step, a point of inflection there. And now we can try to draw this out. So we're going to start in quadrant 3 in the negatives. That way, as x approaches -infinity, y also approaches -infinity. And then I go to this local maximum. I come through, and as I approach -1, I know it's a point of inflection. So I'm gonna try to show that as best as I can. It's not gonna be the best since that value at -0.5 is so close to the y-axis. But here it is. I'm gonna go through that point, come back up to the origin. The origin is nothing fancy. So I'm just going to pass through, go through the point at 1.5, and when I get to 3, I'm going to curve up and jump up. And there's our function. So just to recap here, because it was in factored form, we got our zeros really nicely. Any x-intercept with an order of 1 for the factor, we're just passing through. An order of 2, we're jumping off, like we did here at 3. We just jumped off that x-intercept, we stayed in the positive area. And an order of 3 was a point of inflection. Hard to see here, but we had one at -1. We also found our y-intercept. In this case, it didn't give us any extra point for accuracy, but there it is. Using our degree, so the addition of all of these exponents, and our leading coefficient sign, so the fact that we had a positive number out front, we were able to determine our end behaviors. It was odd, which meant that we were either going to go from a quadrant 3 to quadrant 1 type of movement, or if the leading coefficient had been negative, we would be coming from quadrant 2, ending in quadrant 4. Then, just for a bit of accuracy, we found some extrema, whether they were local or absolute. I mean, in this case, when we do look at the big picture, because of these opposite end behaviors, because it's an odd function, we're not going to have any absolute max and mins. So we found some local max and mins, and then we were able to put it all together with this sketch. So let's try another one. Here we have g of x. And again, we are going to start with our zeros. Now, if you want to pause this video, get your zeros on your own, determine what kind of zero it is, if it's a jump, inflection, or just a pass through, go ahead and then come back once you've figured that out. So for our zeros, we have +4, 0, which is a jump. We have 2, 0, which is a point of inflection because it's an order 3. For x plus 3, -3, 0, another jump because of that exponent of 2. And then we have -5, 0, just a pass through. So I'm going to plot these points. 4, 2, -3, -5. Now I'm going to find my y-intercept by setting x equal to 0 and evaluating. If you'd like to pause here and come back, please go ahead. Here we go, g at 0. We're setting all of those x's equal to 0 and punching it into our calculator. I will show the long way here. And we get 5,760. I'm not going to plot this point just yet because I'm not sure what my scale should be. My extrema later on will determine that. Next, my degree. If you want to take a pause, identify the degree, the leading coefficient, and determine what you think the end behaviors will be. Pause and come back. Our degree, 2 plus 3 plus 2 plus 1 is 8. So we have an even degree, so that means our end behaviors are either going to be both going to positive infinity or both going to negative infinity. The fact that our leading coefficient is negative means we're going to negative infinity. So we're going to have something like this. Of course, the parts in here are going to be a lot more complicated, but that's going to be our general end behaviors. And now the extrema. So since I've already plotted my x-intercepts, I don't have to show that little number line like I did before. You can if you want, if it helps you organize your work. But I see here I have -5, -3. Halfway is at -4. So I need to evaluate g at -4. I also need a value between -3 and 2. If I add those, I get -1, cut in half, -0.5. So I need to evaluate that. And then between 2 and 4 is 3. So these are the 3 values I need to evaluate to get those local or absolute max and mins. So when I plug in -4 into that original function, I get 13,824. So that's going to help me dictate that scale. So I'm glad I didn't put that y-intercept, or else I might have not been able to fit this very large number. For -0.5, I get approximately 8,898.93. And finally, for 3, I get -288. So seeing as I need my scale to reach 13,000, I'm just going to go up to 14,000. That gives me an idea. And I'm just going to say every tick mark is going to be worth 2,000. So 2,000, 4,000, 6, 8, 10,000, 12,000, 14,000 up at the top here. And then that's going to make this -2,000, which is, I don't need to label more because my lowest number is -288. And now I can start plotting some points. So at -4, we want to be at almost 14,000. So maybe something like that. At -0.5, we want to be almost at 9,000. So 2, 4, 6, 8, something like that. Our y-intercept, 0, 5,760. So something like that. And at 3, we want to be at -288. Because of this scale, we are going to be pretty close to the y-axis, and here we are. So I have all of my points plotted. Now I just need to draw it. I'm going to refresh on my end behaviors here. So I need to start and end in the negatives, which means I'm going to come down from here. I'm going to go through -5 to reach this, looks like an absolute maximum. And then I'm going to come back down at -3. And we have to remember, -3 was a jump, so I'm going to jump off. I'm going to hit that point at -0.5, come down to the y-intercept, then get to 2, which is a point of inflection. So I'm going to have to do a little kind of step here. Come to this point, come back up at 4, and at 4 we're jumping off. So we're going to have a jump at -3, and at 4, a point of inflection at 2. It's going to look a little strange here, trying to connect these points while also doing a point of inflection. Now keep in mind, this point here is estimated, so it might look a little bit funkier than what the actual function looks like, but we'll get a general idea to it. So we're starting in the negatives. We're coming up to this maximum. We're coming down to -3 and jumping off because we want to be able to pass through this local maximum and pass through our y-intercept. And then we somehow need to head to 2 as a point of inflection. Come here, come up to 4, and then jump down. And there's our double negative end behaviors. So there's a rough sketch, some accuracy. Like I said, these points here are estimates for us, but in general, this is what the function g of x would look like. So to make sure you are successful with these polynomial functions, it is important that you do a lot of setup beforehand. Identify your zeros, interpret them. Identify your y-intercept. Identify the degree and leading coefficient and interpret that. What are the end behaviors? That way you already have an idea of what this function will look like. And then just for a little bit of accuracy or estimated accuracy, find those extrema. And that's it.